Good to go, Sean.
Wonderful. Great. Thank you so much, Sean. Welcome everyone to the Open Wallet Foundation Wallet Interoperability Special Interest Group call for September, September 8th, 2025. Today on the agenda, we will hear from Abhi Shellett and Matteo Frigo from Google about LongfellowZK. So really looking forward to this presentation today. Thank you so much for joining us. We are recording this call. It will be posted on the meeting page later today. We are following the Linux Foundation antitrust policy and the Open Wallet Foundation Code of Conduct. Let's see. And as we start off the call, we always like to take a minute to see if there are any new people joining the call who would like to introduce themselves and talk about what they're interested in this space or working on. And as well, if anybody has any introductions, now would be a great time to hop off the mic for that. All right. Let's see if there are no announcements or introductions. We can jump into some quick project updates on Akapai. Let's see, Stephen, I don't know if you want to jump in here. I know we've had a very short break there. I know there was some discussion on Akapai Deep Wiki documentation and then RC 1.3.2. Yeah, anything you wanted to call out there, Stephen?
1.3.2 did get released, so it's official. We also, with that, bumped it to being an LTS, so it is now the long-term support. Other news is some bigger changes are coming in the next release. We're almost certainly not going to do another incremental, but rather jump to the new ones with storage updates, revocation updates, and things like that. So things are moving forward. And
Awesome.
we will have a maintainers call meeting tomorrow to check on things.
Cool. And do you know where things are at with the Canon PR?
That's the one that's moving forward. The storage
Right.
updates is Canon. So that's the big change with how non-key management storage is handled within Akapai, and that's coming soon.
Right.
Definitely making progress.
Awesome.
Good progress is being made on that PR with both feedback coming and updates from the developers happening on a regular
Awesome.
basis.
Cool. Sounds great. That's awesome to hear. Let's see. Are there any other project updates from any of the projects we have listed here or others that anybody would like to share?
The other one I'll mention is Credo is still lots of updates happening with that. The 06 release that is in alpha right now is getting pretty close with a number of updates, readjustments of what's in core and what's module and things like that. So lots of evolution happening with Credo.
Yeah, and also we have released the 05/17th.
Oh, good. Awesome.
Yeah, which is the first one that supports the WebVH for the resolver, right?
Yeah. Excellent. Thank you. Thanks for doing that,
Awesome.
Ariel.
Awesome. Thank you. All right, let's see. Any other project updates? And as well, if you would like to put your name on the attendees list here to record your attendance to the call, that is very welcome as well. Let's see, looking ahead as well to upcoming topics in the next few weeks, we're going to hear from Stephen Curran and Patrick St. Louis about DidWebVH. So looking forward to that, as well as digging into the trust spanning protocol and UNICC ID solutions journey and vision. So looking forward to those as well. All right. Let's see. With that, are there any other announcements, project updates, or introductions that anybody would like to give before we jump into the presentation?
Hey, Shar. For the maintainers on the call, the Open Wallet Foundation is looking to do a maintainer summit in October. We are currently working on the timing of that. Do we do it before IIW so we can have lead-in conversations? Do we do it at IIW? If we can get enough folks who are going to be in person, so there should be an email or two coming out in the next day or so. That's it. Thanks, Shar.
Great. Thanks for that update. All right, let's see. With that, I will go ahead and pass the screen share back over and yeah, pass it over to Abhi and Matteo. Thank you again so much for joining us.
Thank you, Char, and thank you, Open Wallet Foundation, for inviting us to this forum to discuss our work. So Matteo is in Rome this week, and so I thought I would begin with this painting by Caravaggio. And the reason it has relevance here is because the main character, well, there are many ways to interpret this famous painting of Caravaggio, and the way I interpret it today is that this guy over here, the main character, he's basically facing a wallet interoperability issue here as he's dealing with the tax collection that is the figure of the main type of thing. And another main figure that happens to deal with wallet issues all the time is our famous Erica, and she has her credential here. She's tired of carrying her plastic credential, and she fears uploading pictures of it. So many websites today ask you if you want to verify some aspect of your identity, that you're asked to basically upload a picture of your ID. And she, of course, does not prefer doing that. She fears that. And in fact, many people, for example, on this particular forum, this person says, there are some sites that ask me to send a copy of my ID. Here are some examples. I'm very hesitant to do that. Has anybody ever dealt with this without having to upload a picture of your ID? And so we get the sense that this is a classic problem, and I think many of the people on the forum are on this call are aware of that. I'm going to basically organize the rest of this talk. The first half is basically explaining the problem and the privacy problems. I think many of you are aware of this, but if I figure I'll go through it quickly, and please interrupt if you have any questions about that. And then the second half will be our opinionated solution to the problem, the LongfellowZK system, the design decisions behind it, some of its performance details, and some of the things that we're currently working on. And one of those things are, many of these topics intersect quite well with, in fact, the slide that Shar just had about, for example, the group that's working on STJOT. We have some suggestions and ideas about that to make it easier to do ZK, and I'll talk about those in our experiments. And of course, we'd appreciate your feedback and help in getting some of those changes propagated. So back to Erica's problem. So she doesn't want to upload an image of her digital credential like many people, and so enter the digital credential. This is going to be a signature that is private to you, that's held on your phone, and that's issued by, let's say, a government or some sort of issuer authority. And what can you do with such a credential? Well, you can present it online. So you can present it both online and in person. That's envisioned in the way that this field is emerging. But we're today going to focus on the online flow. And in cryptography literature, this idea of presenting a digital credential has been around for quite a bit of time, at least 40 years, with Chom's paper creating this idea of a pseudonym, and a subsequent work that has created instantiations and so forth. All of those works in the literature talk about this notion of selective disclosure. So you don't want to, when you disclose your identity, you don't want to disclose all of the information on it. You would like to select which parts of the identity attributes you'd like to disclose. In this case, in many cases, things like age over 18 or your particular zip code of residence and so forth. Some very small aspect of your identity might be the attribute that you want to share. And all of the protocols that we're going to discuss, in fact, have this notion of selective disclosure, some in a weaker form than others. And of course, our goal here is to achieve the strongest notion of this property. So at least I could find work starting on this topic in ISO, at least starting from 2016. And in fact, this idea of selective disclosure was immediately in their first, if you go and look at their archives, their first document of their first version of their proposal begins with the idea that you have to make sure you support selective release. And at this point in the design process at ISO, no cryptographers were involved. And so I give them a lot of credit for first identifying this as a relevant property and then designing protocols that achieve some notion of it without actually having cryptographers involved. So that they achieve a weak notion of it that's reasonable, but it has a privacy flaw that I'm going to talk about in the next few slides here. So let's talk about the protocol, which starting in 2016 they developed, and it's deployed, and it's quite sophisticated. And now there are other versions of this protocol that are like STJOT and W3C verifiable credentials that have different syntax but achieve very similar privacy properties. So the way this protocol works, there's a relying party, an RP, that makes a request, for example, in this case, age over 18, and they send over some information like the request and some extra auxiliary information. And in the MDoc legacy protocol, the user or their device basically responds with this full MDoc with what I'm calling a pre-image of the attribute that they're showing, and then again, some auxiliary information that we'll talk about later. This statement, this protocol flow is meant to capture formally this informal statement that the prover, the user, is trying to convince the verifier, the relying party, that, for example, the state of California has produced a signature on a document that's stored on my cell phone that includes this particular attribute. That's kind of the informal statement, and the way they embody that or implement that statement is essentially this protocol. And then at the end of this protocol, the relying party basically verifies these 5 steps. They check signatures, they parse documents, they verify signatures, they verify pre-images of hashes, and they verify some sort of expiry condition values at a high level. Now, how does an MDoc actually look in order to understand this protocol to the next level? This is a sample MDoc, and what I'm highlighting here in green is the salted hash aspect. I think everybody on the call is familiar with this idea of a salted hash. And so this green value right here, this salted hash, corresponds to the SHA-256 of this red message. And this red message is the pre-image, and it includes, for example, a random salt, this part that's in gray, as well as the age over 18, the attribute that's being claimed, as well as the value of that attribute. So if I'm just given the MDoc, and here notice this MDoc has about 34 attributes in it. If I just look at these green strings cryptographically hide the attributes that they stand for. However, if I give you the pre-image, this red string, then of course the relying party can hash the red string, verify that it's equal to the green string, and that the green string is included in the MDoc, and that the MDoc is signed by the state issuer. That's kind of how this soundness property that California has indicated that I'm age over 18 is implemented in this particular protocol. Okay. So indeed, the full version of the protocol is the relying party makes a question like age over 18, and the user responds with that full MDoc, the entire MDoc that I showed on the previous slide, the pre-image for the attributes that they want to reveal. And again, this auxiliary information, which I'll talk to you about in just a second. That's the MDoc property. I think most people are familiar with this type of thing, but are there any questions on this? Okay, so what creates the privacy problem? Well, there is a natural concern with issuers about the soundness of such a digital credential system. And anytime you have a credential that's like digital as opposed to like a piece of plastic, you have to worry about an adversary copying the credential of one user onto a different user and then using that copied credential to basically make claims and present. And of course, if you root a device, maybe you can essentially copy this information. So to get around that, the issuers of these, the MDoc, the ISO protocol, they rely on trusted hardware, specifically this notion of device binding. They want to informally ensure that every issued credential can only be used on the single device to which it was issued. And the consequence of this type of thing is if you try to do this device binding, you put major constraints on the type of anonymous credential and the type of zero knowledge proof system that you can deploy in practice. And again, this trusted hardware, it relies on essentially a secure element, a piece of hardware that's on your phone that has the ability to create certain keys, like for example, ECDSA signing keys, which are very difficult to extract from the phone. And so their security property is that they can only stay on the phone. The secure element, if you have the right operating system authorization, then you can make API calls to the secure element and you can ask it to sign messages, but you can't actually extract the key and sign messages off the device. Now, the problem is that, so this video essentially shows an onboarding process. I'm going to go ahead and skip the video and basically get to the point that because this ISO protocol requires this type of device binding, it makes use of these very low-level aspects of both Android and iOS phones, the secure element and an API to access that secure element, and changing those layers, changing the hardware on every deployed phone, and then changing the API level of like essentially the deployed phone base. That is a big task, and it'll take many, many years, 5 years, I think more like 15 years. And therein lies one of the problems. So this idea of having a device-bound key in the MDoc, if we go back to this MDoc statement, remember the green was the salted hash. This yellow part is the device-bound public key that is used to implement this. So the state of California or the state of Massachusetts, after I do my onboarding, after I onboard my credential onto my phone, essentially it will get a copy of my device public key, and it will incorporate that copy into the credential that it signs. So this document is the document that's signed, and it incorporates this yellow string, which is my device public key. Now herein lie, so again, the overall presentation protocol now, the flow is that the relying party asks for this age over 18. It also sends this nonce over, okay? And the response includes, as I said before, the full MDoc, the pre-image of age over 18, and now a signature by the device public key over this transcript or this nonce. So that kind of, essentially because this is happening, because the nonce should, with very high probability, be different in every time a relying party asks for such a presentation from any device, it's going to randomly select this nonce, and this nonce is going to be different. And so essentially the user is going to have to prove that they have access to the device that can create signature under the device public key on this random message. It can't just copy the transcript of a previous protocol flow. Okay. Now, unfortunately, while this device public key solves one aspect of the problem, it solves the device binding aspect. This problem creates another one, which is it breaks the unlinkability. So this device public key, because it's part of your credential, acts, and because it's impossible to change this without actually creating a new secret key on your phone, this yellow part becomes essentially a tracker, a super cookie that relying parties can use to basically track you across the internet. So if a user makes a presentation to relying party 1 and then to a relying party 2, if these two service providers, if they correlate their information, they'll be able to say that, in fact, my session 17 and your session 95, because they include the same yellow values in the full MDoc, they correspond to the same user. And this tracking problem is a substantial and big one to solve. Even if we force users to essentially use a different key for this service provider than the key that we use for this service provider. So we essentially give each user several thousand credentials and have them use each credential for only one particular relying party site. There's still a problem in that the issuer, or for example, the Department of Motor Vehicles or whatnot, since they sign all of these device public keys, they can correlate essentially, if they subpoena, for example, if they work together with the service provider or the relying party, they can correlate, they can look at the full MDoc and then figure out exactly which user went to which particular service party or relying party site. And this type of tracking is a serious privacy issue. Now, I think it's commendable that this protocol that was developed without cryptographer input, it achieves quite a lot of interesting properties, and it's quite efficient and interesting, but it has this one big security problem, which is that either relying parties or the issuer and a relying party can collude to track who is using their credential at which website. And that's a problem. However, this protocol is deployed, this legacy protocol is deployed today, and it's a big ask to essentially remove this implementation from the ecosystem and try to replace it with a different one. And so the approach that we've taken in Longfellow is to essentially build a new anonymous credential system that layers on top of this system. So we take this legacy MDOC protocol and we build a zero-knowledge proof system that can essentially be applied atop this protocol as well as others like STJOT, et cetera. And it solves all of the privacy issues. It means that a user with only one credential on their phone can use that credential to essentially selectively disclose attributes at any number of relying party websites, and they can be rest assured that no relying party and no issuer, no collusion among any subset of those can essentially track their user. Now, of course, if you disclose your first name and your last name and your address to relying party 1 and to relying party 2, they can use the information that's been sent to them to essentially correlate and track you. However, the protocol itself cannot be used to track the user, if that makes sense. So the design that we're changing, that we're proposing, is that we still keep the flow of the original MDOC or STJOT protocol. So the relying party makes a request, but now instead of sending the MDOC, the salted pre-image, and other information, instead we send a zero-knowledge proof as well as the time and essentially the original transcript information. And we prove in zero knowledge that all 5 of the checks that would have been done before are satisfiable. We give zero knowledge proof that the checks that the relying party would have done actually would have verified. And that's simple to deploy. All it requires is changing the response that the MDOC protocol has. Instead of sending the original MDOC response in clear text, you send a ZK proof. And that makes it very simple to implement or layer this on top of any legacy protocol. Now, some of the differences. Now, we built our Longfellow zero knowledge system. There are lots of design choices that you can make for zero knowledge. We built our system with this problem in mind. How can we build a system that runs on a user's phone and can answer questions like the ones that arise in this legacy protocol? Those were the design constraints. And in fact, that's very different than the rest of the literature or rest of the work that many people are working on in ZK. And in particular, instead of focusing on the succinctness property, which you might have heard of snark or stark and so forth, those type of proofs, which are meant for like blockchain applications, they really require the verifier to be more efficient than the prover, and they require really small proofs that a small verifier can verify. In contrast, in our setting, it's a really small prover, i.e. your phone, and it's a really big verifier, i.e. a server that's been run by a relying party website. And so that's one of the main differences. We don't necessarily need to satisfy that requirement. Of course, we also don't want to use things like trusted parameters. We don't want to ignore the previous work. We don't want the issuers to be involved in internet scale activity, so we don't want them to have to be involved in the online flow for a particular protocol. We want post-quantum security. We don't want to use any assumptions like elliptic curves for the zero-knowledge proof system that are not post-quantum secure. And of course, we make a bunch of engineering trade-offs. The prior work in this area couldn't really resolve any of these issues. They were either, if you look at the work that was meant for blockchains and just applied to this problem, it takes about 140 seconds to produce a proof, and it required essentially a gigabyte of a trusted parameter. Starks also didn't work. Other contemporaneous academic work, either too slow, too big, or required trusted parameters. None of the prior work could satisfy the requirements that we needed for this problem. And that's why we developed Longfellow zero knowledge. We looked at essentially the matrix of zero knowledge proof systems and decisions that you can kind of make. I'm going to kind of skip over this so we can get kind of to the second half of this conversation. We use an old recipe, and to make our Longfellow, the aspects that are novel to our scheme are essentially the selection of the components that we put into this particular recipe. And we decide to use this notion of a layered sum check, and we pick a specific commitment zero knowledge proof system called Ligero. So what's our contribution here is essentially observing that these two can be combined and combining them in a right way that produces a very quick, efficient proof system. To give a nutshell of how our proof system works, essentially the first message of the proof system is to commit using the Ligero proof system to the witness that we have, as well as some sort of pad that we use to encrypt our transcript, to encrypt an aspect of the proof. So we first send over a commitment. Then we run a sum check protocol, which is this layered sum check protocol. The circuit that we want to verify, see right here, we run that sum check transcript protocol on the circuit, on the public statement, the X part of it, and the private part. And of course, the verifier only gets the circuit and the public part of this. And the one main change we make to this layered sum check protocol is that instead of, whenever the protocol says send a message MI, like the ith message is, let's say, MI, instead of sending that message, we actually send MI XOR this one-time pad. And we made sure that we committed enough pad here to make sure that we could cover the full transcript of this sum check protocol. And then finally, we use the Ligero prover to prove that with respect to the commitment and the transcript that was sent in the second step, the sum check verifier would have accepted that transcript. And so we use that. This is the inner statement that the sum check verifier would have accepted this statement. And we use the Ligero proof system to generate constraints from that inner statement. And then, of course, the verifier uses the Ligero verifier to check this inner statement on the relying proof. And this is kind of has its basis in this old work from 2017. And why do we do this? So, of course, this is the full interactive version of the protocol. We can use the fiat Shamir to make it the two-message protocol that's necessary for this protocol flow and everything. In a nutshell, why do we choose to do it this way? And that is because most other transparent argument systems, like Ligero or Starkware or anything else that does not require a trusted setup parameter, it has a constraint that one has to commit to all of the, if this is the circuit that one is trying to verify, all of these other schemes require you to commit to all of the internal wires of the circuit, all of the internal multiplications of the circuit. And the difference with our approach, if we first apply this layered sum check to this transcript, we actually only have to commit to this input layer of the circuit, as well as a very small sum check transcript. That's that pad value that I was basically saying before. And based on properties of sum check, that pad, that transcript for sum check is substantially smaller than this full circuit. And so that's essentially the ultimate reason why our design is as it is because we just have to commit to a smaller amount of information. And commitment is one of the most expensive tasks for these zero knowledge proof systems. When you, of course, apply our mechanism, now the commitment no longer becomes the expensive part of it. There are other aspects that become the bottleneck. But if you don't, if you're in this regime, then the commitment to several million wires, which is the size of the kind of circuit that you have to commit to if you want to do this type of MDOC thing, that becomes prohibitively expensive. Okay, so let me give you a few details here. So if you're verifying an ECDSA signature, okay, these are the 4 steps that allow you to derive a circuit for verifying that signature. One of the problems, and this is one of the problems with all prior works in this field, is that this circuit verification happens over, for example, if you're working with the P256 ECDSA over the P256 elliptic curve, the finite field that is defined for this curve, if you look at its factorization here, it does not have enough roots of unity, which is this 2 value right here. It doesn't have enough roots of unity to actually support an efficient FFT or number theoretic transform. We get around this through 2 ways. The first simple way is to observe that the quadratic extension, in fact, does have enough roots of unity. And that's what our current implementation does. We're working on an implementation to do an even faster approach that makes this particular step even faster. And if you use the correct math, then the circuit size that's needed to verify an ECDSA is actually very small, something like 50,000 constraints or wires versus millions that the CIRCOM ECDSA or prior approaches like the Starkware approach basically required. So we had essentially 50x improvement over the size of the circuit. And that's what makes it very efficient for us. We're the first scheme that allows you to give an efficient proof of possession of an ECDSA signature. That's what this statement is right here. Some of the benchmarks are that we can essentially produce them in about 60 milliseconds on, this is essentially a cloud-based x86 and essentially 80 milliseconds on a Pixel. If you do it on a Mac, it's about 35 milliseconds. And if you do it on an iPhone, it's also about this particular 35 milliseconds. And so this is one of the illustrations of how our approach significantly improves over prior work. Again, CIRCOM taking 140 seconds, the best academic work taking about a second, and our approach taking about 60 milliseconds. Okay, so same goes for SHA-256. So if you want to prove that you have the pre-image of a SHA-256 hash, essentially, our approach can essentially do that in 11 milliseconds on a cloud-based instance. And if you scale that up, it becomes around maybe like 200 milliseconds for a fairly large message. And if you do the same sort of scheme with Ligero, it's about, again, a factor of 26 times slower. And that is, again, because our approach commits to a fewer number of values. And of course, this gets slightly better if you run it on, for example, Mac hardware instead of older hardware. So let's get back to the original problem. If you have this legacy MDoc statement where you need to verify signatures, you need to parse documents, and you need to check expiry conditions, we translate that into this zero-knowledge statement, which I'll let you take a look at. Compute. You're verifying that essentially this value E1, this hidden value E1 is the SHA of your document, that you have a signature on this particular SHA value that verifies that when you parse the document, you get this age, and you look at the age over 18 aspect of it, that there's a pre-image that if you hash produces exactly the right values. There's a device public key in that same MDoc, and when you verify the transcript, you know a signature on that transcript that verifies under the device public key. And again, the time start, time end, essentially, and time now have essentially indicate that this document is not has not expired. Now, this zero-knowledge statement takes about 7.2 million wires or constraints. It takes about 3 million quads, which is one of the other ideas we have for the way we represent circuits. So it saves about a factor of 2 if we do it in the way that we do, as opposed to the way other approaches to SumJack take this. About 600,000 or 10% of the wires, a little bit less than 10% are in, we also do this over 2 finite fields. They're in the P256 field, and about 90% of the wires are in this GF2 to the 128 field. Essentially, that's reflecting that SHA-256 represents about 90% of the work, slightly more than 90% of the work of verifying this particular circuit. And you can use these things and take your other favorite ZK proof system, run this through there, and figure out essentially how much it would take them to essentially deal with this statement. Here's a short little demo if you haven't seen this. What I'm demonstrating here is essentially a website that will request your age over 18, or I think your birthday in this particular thing. And over here on the right is essentially a screen capture of the phone. And this is going to be a cross-device presentation, one of the hardest cases to basically handle. And we use the same passkey mechanism. So a QR code shows up from your Chrome browser, and then you're supposed to scan it with your phone, and that engages the wallet. So after the connection made, your wallet shows up, And now you can select, for example, from Google Wallet, the wallet you want to do. You're asked to confirm that, in fact, that you want to share this particular attribute. You're asked for a biometric authentication, and then a connection is again set up with the phone, and the proof is basically sent over. Now, one aspect of this is that and there it is, it's done. One aspect of it is that every flow like this requires you to do a biometric authentication, as well as, again, for a human to read and confirm that the information that they are sending is what they expect to be sending. And those aspects of it, the confirmation, etc., those aspects essentially hide the latency of the proof, and the proof takes little under a second. So between 800, somewhere around 800 milliseconds now in the latest version of this. So that is where the first version of our Longfellow system is. I sort of explained why we designed it the way we did. So what problem we're trying to solve, why we designed it the way we did, because essentially we want to reduce the number of values that you have to commit to by doing this layering. And we also need to work in two finite fields in order to do things like verifying legacy ECDSA signatures as well as verifying SHA-256. Those are some of the innovations. And now these are some of the other requirements that we're trying to handle for interoperability and for other use cases. So some of these, like credential revocation, handling pseudonyms, hiding the list of issuers, handling new formats like JOT. So we have some improvement on SD JOT called ZK JOT. And of course, we have some alternatives, some reasons why things like BBS Sharp, and all of its other alternatives don't necessarily work. So I want to kind of ask if anybody has any questions at this point, or wants to hear about some specific aspects of Longfellow. Let me see if anybody's on chat. Please just unmute and ask if there are any questions.
Abhi, I'll jump in.
Yep.
As always, awesome to hear this. Love to hear where you are on pseudonyms. That's a big one. We've had and revocation. I think I've seen your revocation, but if there's time, a brief overview of if you've made progress on pseudonyms, though.
Yeah, sure. So in fact, yes, we are. Let me skip over the revocation part, and the JOT part I'll come back to in a second as well. The pseudonyms are actually very easy for us to support. So in essence, if you look at this statement that was, this blue part is kind of that complex ZK statement that I basically showed. The way we imagine pseudonyms is that your MDL document includes this pseudonym seed, which is essentially the hash of some secret. That attribute is basically going to be managed. And right now we're basically worrying about where these things are stored and how you recover them if someone loses their phone. But the principle of it is that essentially the credential includes this pseudonym seed. That's a new attribute that's added to the credential. And then every time you want to create a new pseudonym, all you do is the phone will take the secret that's stored in the credential, apply some pseudorandom function to the secret, and then some context string. The context string could be essentially a concatenation of the URL or the RP identifier, whatever you use to identify the relying party website, as well as some number. So for example, that could be time of day, or that could be like the first credential, the second credential, the fourth credential, etc. Some context information that's used to create a particular session. So a website might say that I only want each user to create one pseudonym. So that means that the context essentially is fixed for all use cases. It could be that there's one master context, and then for every forum or for every discussion thread, people can create new pseudonyms for that particular thread. Those are some of the design decisions. But the actual changing of the zero knowledge proof system, basically we're adding one hash, and so that's like if right now in our system, that's about 3% increase in the time it takes to handle this value right here, and then one evaluation of a pseudorandom function. So you could use something like AES, or you could use some sort of like HMAC or some sort of like hash-based system again, and that will add 1 or 2 again hashes. So again, it's on the order of 3 to 10% that's added to the running time of our protocol if we want to support a pseudonym. Now again, this pseudonym right here is what would be publicly released, and every time you either log in or you change an attribute, you would essentially include the normal proof statement as well as these 2 extra green statements. Now, we haven't implemented this fully. We've only designed it, and right now we made a proposal that I think Renee Meyerhofer and Anya Lehman are sort of also involved in, and we're going to see essentially what specific design choices, and then I think it'll be it's going to be very easy for us to add this type of aspect. The real problem with the pseudonym is how do we manage this secret? For the pseudonym to be completely unlinkable. Oh, go ahead. You have a question?
No, I was just going to say, it sounds like it's not the cryptography that's the hard part. It's the figuring out how to govern it, how to make it so that the issuer, holder, and verifier coordinate properly the use of that secret.
Absolutely. So the hard work at this point is designing the protocol. So how do you request a pseudonym? How do you request the context? Are you allowed to request a context? How do you prevent RP1 from sending you a context that's, the context of RP2? So again, there are a bunch of system issues that are involved. And I think the biggest one is how do we manage this user secret? So as a cryptographer, and I built a system like this in 2016 called Anonyze that had exactly the same issue. We deployed it to a bunch of undergraduates to basically do course evaluations. And for the pseudonym to work, so essentially you couldn't link your course responses in course 1 to the course responses in course 2, etc. But that required the user to maintain this secret. And even in a small set of 100 undergraduates, there were people among the 100 undergraduates we did this trial with when I was in 2016, there were people that would lose their phone or erase the app or reformat their app or do something that would essentially remove this secret. And that if you remove the secret, you cannot recover the pseudonyms from your previous contexts. If you store the secret on something like Google, then indeed Google knows your secret. And now essentially there is some mechanism for that secret to be used to kind of, Google could technically de-anonymize you on particular websites. Now, of course, we can store this information in some encrypted format in Google, but if someone makes a subpoena or something like that, it's unclear what happens. So one of the big problems is we cannot trust users to maintain this secret, which means wallet providers need to maintain that secret for them. And if wallet providers maintain that secret, then there is some angle for that secret to be extracted and then for pseudonyms to therefore be de-anonymized. And we're figuring out essentially UX to explain this and some sort of system like where maybe a user, if they decide that they are willing to write down the secret on a piece of paper and put that in their safe deposit box, or like make copies across and do their own management, we can allow this. Or we can say, maybe you want to upload this and sort of keep this in encrypted format, so forth. If you have any ideas on how to manage that problem, that I think is one of the biggest deployability issues for this.
Okay. Quick question. Is the secret common across multiple credentials? Or would it be possible that the issuer for a select credential would maintain a consistent identifier for the holder?
Yes. So in this design, this H of secret, this hash of the secret, that's what I would give to my DMV. Now, they can't use this H of secret. They can't undo the hash to recover my secret, but they would maintain this H of secret, and every credential that DMV issues to me would include this particular secret. Now, for example, if I get another credential from my bank, it could or could not be, depending on how I manage it, it could or could not be the same secret. I could, for example, the bank could basically say, please disclose this H of secret from your DMV credential so that we can use the same pseudonym seed across all the credentials. That's a design decision. However, the problem still arises that, even though the DMV uses the same thing, if I have lost my own secret because I lost my phone, then I would have to go through a process with the DMV to say, I need to reset this. I'm going to lose all of my previous accounts. And now the DMV should, going forward, use this other thing. Now, of course,
Yeah,
you have
no.
Yeah, go ahead.
So two things. The what I was thinking was the DMV could itself create the secret
Yeah,
that is bound to that user. So every time they do the, whatever's necessary to authenticate the person, they would then say, okay, well, here's the secret we use for you. So it's not the holder that's holding it, that
yeah.
manages
So
it. It's the DMV. So that's a possibility.
the problem with that is then the DMV can essentially de-anonymize all users. If they know the secret, they can go to a particular website and ask for their logs, and then they can essentially undo
Oh,
this.
they
They can
can.
apply the
Okay.
PRF
Okay.
secret in the context, and then they can figure out your
Okay.
NIM.
Okay. Okay. So that's no good. Okay, good. That's good to
Now,
hear. Good to
you can
understand.
have them
I mean,
contribute something. So you could make the secret like half of it is contributed by the DMV, and it's, they randomly select a half and you can randomly select a half and so forth. And maybe if you do that with like secret sharing, with like you essentially make the DMV contribute half, Google contributes a half, and like maybe the Open Wallet Foundation contributes a third. They maintain that, and so unless all three collude, you can be guaranteed that like nobody can recover. There are these type of schemes that we have in mind too, but again, all of these are engineering complexity. We're trying to figure out what the elegant way to deploy this would be.
yeah. Awesome. Thank you. That was excellent.
Yeah. We also have techniques to, of course, do things like hide. Maybe you don't want to release the fact that you're in Massachusetts. You just want to say that you're one of the 50 United States. That's a very, very simple change for us to do. It adds about 50 milliseconds of proving time for 1,000 signing keys. That includes all US states, all previous versions of those states, all EU states, all previous versions of the EU certificate authority, et cetera, et cetera. One of the issues that I wanted to bring up with interoperability for this particular forum, I don't know if that was interesting to the people on here, but to give us an update on the status. So in ISO, we have asked for modifications to the MDoc document response. That's in draft of the second edition. And that is a specific protocol that changes the MDoc protocol, which allows you to specify, I would like, for the relying party, I would like a zero knowledge proof. And of course, it's also gracefully degrades from ZK back to normal. If, for example, the phone doesn't support it, it'll basically respond with a normal response. So that's in process. For OpenID 4VP, we've implemented one embodiment. It was, of course, inspired by the change here of a way to request zero knowledge. And that embodiment is implemented in Google Wallet, and we are essentially working on documenting that and essentially getting people's feedback on how that flow could be changed. Of course, OpenID 4VP is like a high-level meta protocol. It leaves many decisions to be unstated or designed later, and that's kind of one of the aspects we're in work there. In terms of data formats, the proof. So there's like, how do we format a Merkle tree? How do you format an IOP commitment? That's a type of commitment that's used in all of these transparent proof systems that don't need trusted security parameters. We think that these two statements can be universally, we can universally standardize these two, and they would work. I think we have the optimal embodiment of those two, and that could be applied to any ZK proof system that's in this model. These latter three things, how we serialize our circuits. I mentioned this quad format that we have that's kind of specific to SumCheck, the way that we serialize a Ligero proof, the way we serialize a Longfellow proof, which is a sequence of Ligero proofs applied to this layered SumCheck. Those things we've written down in this IETF document. We'd love to get some feedback from anybody who's interested. But that's essentially where the interoperability questions have. Now, if anybody has some other issues with interoperability or things that you're thinking about, we'd love to hear about aspects that we don't know about right now. If anybody has. So if not, one issue that I do want to bring up is essentially support of JOT. And I noticed that OWF does have a SD-JOT implementation that was on one of Char's bullet points. And I would like, if that is still active work, I would like to get your feedback on this particular suggestion. Is that something that's relevant?
Yeah, and we also have one of the SD-JOT maintainers on the call today, but we can definitely set something up and connect you guys after this call. Absolutely.
Great. So this is a clean JOT, that's standard JOT, right? You have essentially the header in red, the body in this green part, and the signature in this other part. Now, we have essentially taken this format and built in a ZK JOT, essentially a proof that you know strings, the header, the payload, and the signature here, such that essentially the payload of this document contains, for example, age over 18. We've implemented this statement. It's very efficient. It's like this is it's more efficient than, for example, our same. I'll go later on. I have a updated implementation times for this particular statement. It's way more efficient than our MDoc for the same size documents. But we have made one little change. So for example, we call this JOT plus key binding 2. It's the change we've made is to the key binding aspect of the SD-JOT protocol. And so this right here is like a standard JOT, and this right here is the key binding part of it. After this tilde, you essentially have another JOT, another signature on essentially the key binding message. Now, the SD-JOT spec, essentially, section 4.3 of that spec, has these two parts. Okay, so it requires that this the header for this part be KB-JOT. We've changed that. We've changed it so that this header has to be where do I have? Essentially, this header is KB2 to essentially differentiate it. And the second part is that the JOT payload in the SD-JOT spec requires this field called SD hash. And this SD hash field is defined as the hash over this boxed component. And the reason we want to eliminate this is because it requires you to recompute a hash over this particular thing inside the zero-knowledge circuit. And that essentially doubles the working time of this proof system, essentially to recompute this. Moreover, this included SD-JOT doesn't add any security properties. The freshness that's needed for this key binding, that's provided by the nonce and the odd and the IAT fields. So this extra field doesn't really add anything. And moreover, unfortunately, if you don't handle this properly, you cannot reveal this SD hash to the relying party, because again, that it becomes a tracking cookie if you reveal it directly, because this field, the payload part of your document essentially is fixed as long as your identity attributes are fixed. And so that's a problem with this SD hash. What we've suggested with this KB2 thing is just simply remove it from the part of the key binding JOT that's produced there. And so that's essentially an omission. It doesn't affect any security. We've proposed this to the IETF part of that handles the SD-JOT spec. They say they can't make a change this late in the field. Like for the next iteration, it can be considered, but it can't be handled in this iteration. And so essentially one of the things that we're trying to lobby for is unofficial sort of inclusion of this KB2, this key binding 2 version that supports our SD-JOT document. That way, essentially, we can get ZK for this JOT type of document very efficiently, much faster than MDoc, and essentially compliant with all of the SD-JOT interpretation libraries. Currently, of course, we wouldn't comply because we would be missing that SD-JOT. So if you go to the sdjot.js website and take our document right here and paste it there, it says it's invalid because it's missing that SD hash. So I'd love to get your opinion on how feasible that is for us to basically support, efficiently support this kind of JOT-based credential format.
So this is usually the part of the call where I ask our presenters, what do you need and how can we help? I want to add a third part to that. Where can we give this feedback? Abhi, you mentioned a couple times in the call that you're looking for feedback on some of this. Where's the best place for us to get you this feedback? Because that sounds like, or the best place is.
Yeah, so there are a number of things we can do. We have a GitHub. So we could create an issue and we could specifically outline this particular issue. And if that's the way we want to collect feedback, we can do that. Of course, we can also do that just over email informally. And basically, we want to get into a conversation with the people who maintain this library to see how, like, what objections do they have? What things can we change? I don't think from cryptographically, this isn't a big ask. And I can't see any reasons why it would be objectionable. And Brian Campbell, I think one of the maintainers on the IETF, he said that he also, strongly supports this change. It's just that they can't make the changes officially in the document for procedural reasons, until, for example, the next iteration comes.
That makes total sense. Anyone else have a question? We've got about 4 or 5 minutes left.
I got one question.
Yes.
Do you hear me? Yeah, thank you. Thank you for the great presentation. I'm actually a maintainer of SD JavaScript project in Open Wallet Foundation. And in my point of view, the removal of SD hash could be a good solution. So the RP send the nonce to the holder, that holder sign it, the
Yep.
jot with the nonce. So I guess that's pretty much for the security of the cryptographic, the session things. So I think we could, our maintainers could simply fork the existing library and test it with the SD jot with your KB2 spec in order to test the ZK feature on SD jot. I guess we could do that easily. So
Excellent.
if you want, we can proceed it within a month or a few weeks. Yeah.
Yeah, so Lucas, let me connect with you offline. We'd love to begin doing these experiments and essentially testing to make sure that nothing breaks, and then basically get this JOT plus KB2 type of thing. First step towards standardization is making sure that some implementation supports it and that it's backwards compatible, where it needs to be.
Abhi, I'm going to connect you and Lucas and Matteo offline the minute this call.
Oh, excellent. Thank you. Thank you.
Yeah, great.
Abhi, are you open to sharing these slides if I could post them on the meeting page later?
Absolutely.
Sounds good. Wait, yeah, I'll email you afterwards to go. So
I'll make
you.
a PDF and then send that to you.
That'd be
Great,
awesome.
great.
Romek has his
Thank
hand
you.
raised. Romek, you might be the last question. Go for it.
Okay. On the side of Lucas, thank you, Lucas, for joining us. But the Jose side, currently the Open Wallet Foundation uses about 6 different Jose systems. And how do you plan to actually support that from the Jose side? Because I saw there was a change in Jose as well as the SD jot. So there's about 6 different Jose. So we don't have an OWF Jose implementation. We use various open source versions, Parva for SD jot, Jose in parts of things like Akapai. How do we address that on the Jose side? Is that going to need any changes from us?
So I don't think so, because
Can you show me the Jose change? Yes, that you were doing as well, because there was an SD jot, there was a jot change, there was a Jose change as well.
I don't know. We don't need a Jose change. Like, the way that signatures are verified is not changing at all.
Can you go back a slide, please? Sorry, there was a change in Jose as well as in jot. Yeah, this bit. Yeah, so there's a.
Oh, I see. Yes, you mean we need to support in Jose
Yes,
might, for example.
that's what I'm saying, because
support...
all our Open Wallet Foundation systems are using various versions of Jose from open source, and it's almost like, apart from, I'm doing sort of interop looking at this for using the different versions. I'm looking at this from a Jose point of view, and is there any changes going to need to be done on that, because we're using other people's Jose implementations currently?
Okay, good point. So essentially, having this library support this change requires first having each of the 6 Jose libraries add the change where they support KB2.
Yes.
If they, for example, make a restriction on the type of the object that they support. Maybe all libraries may not do that, but yeah, I see your point now. Yeah, thanks for raising that.
Because what you've got here in the Open Wallet Foundation is they generally using the standard JavaScript Jose implementation with the Jose in NPM. Lucas is using Parva. So there is different versions because we've got different languages being supported here doing different things. It's one of the interop discussions going on here about Jose as being one of the areas we don't actually have a Jose implementation as is in the OWF, and it's something to be discussed later. So yes, there's about 4 different versions here, and I suspect there's others. There's things like the Cisco version, for example.
Yep. Okay. Thanks for pointing that out.
Thank you. Yeah, thank you for your answer.
I think we're out of time now. I appreciate all of your questions and your attention, and please feel free to reach out to Matteo or me. And we look forward to working together with everybody, essentially in the Open Wallet Foundation.
Absolutely. Thank you so much, Abhi and Matteo, for joining the call. Really appreciate your time today and for the presentation and discussion. So thank you. Thanks everybody for joining the call. Join us next week as well to hear from Stephen Kern and Patrick St. Louis about Did WebVH. And yeah, thank you so much everybody for a great call. Thanks, Matteo and Abhi. One more thing.
Let me make one more point, which is that our library is integrated into the multipaths library. So Corey Barker, one of the Google engineers, he's taken our open source library and ported it, and I believe he's pushed the contributions to multipaths, which is in Open Wallet Foundation. So there's an open source integration available.
Awesome. Cool. Thank you for making that note. That's really helpful to hear. Great.
All righty.
Awesome.
Thank you, Matteo.
Great.
Thank you, Abhi. And thank you, everybody, for joining us today. This video, when it encodes, will go up on the Open Wallet Foundation YouTube under the Wallet Interop SIG playlist, and we'll put a link as well into the Wiki page, which was shared earlier. But I want to thank everybody for joining us, and especially our guest speakers. This was fantastic.
Thank you.
Thank you so much.
Great day, everybody.
Really appreciate it. Thank you. Bye.
Bye.